All right. I don't know if it's clear that side so that we can start.
Yeah, I can see the question.
Okay. So here we are given now a spring. Now you can see now the spring is now complex. They've made it more interesting now. Instead of one object which is oscillating, how many objects are now oscillating?
2.
There are 2 now.
Mm.
So it's no longer that simple one which we're having, which was only having one mass. So
Okay.
one, you can see a different one. All right. However, the method of approach is just the same, but you must take note of things that have been mentioned. Let's read the question. It's saying 2 objects. So these are the objects which they are referring to. 2 objects, A and B. Each mass M. So which means each they are having a mass M. In other words, they are identical, isn't it?
Yeah.
Are connected by springs as shown in figure below. So these masses are connected by spring. Right? The coupling spring. The coupling spring, what does the coupling spring mean? It means this spring which is at the middle here, it's joining. This is the spring that is joining the other one.
Those round black things.
Yes, those are the masses.
Mm.
Black things. They are your masses. It's representing an object. Yeah. They are the round black things. So the coupling spring is the one which is here at the middle here, this spring. Remember, this spring is mounted here. Can you see? And then this is also mounted here on the left. This one is mounted on the right. Then also there is a spring that is coupling them, joining them together, which is the middle one. That is why it's a coupling one.
Coupling, does it mean joining?
Yes, exactly.
Oh,
Joining those two springs.
That word for many times, but I didn't understand what it means.
Joining, just like a couple. If you are a couple, what does it mean?
We are connected.
They are connected. Yeah, you see, that is where it's coming from.
Okay.
Coupling. Or they are joining those two. So they are joining the spring on the right, this one, and then the spring on the left, this one, with the spring at the middle, which is the coupling spring. That is the one.
Yeah.
So this coupling spring, there's a constant which is different from the other springs which are on the either left or right. So the coupling spring is its own constant. Remember, a spring constant when we're talking about the force of a spring. We said the force of a spring, it's F. F is equals to minus Kx. This is the force inside the spring. So the restoring force. So which means K, if your force is in newtons, so you want a newton force, is equals to minus the direction of the restoring force. Spring constant, it's in newtons per meter. That is the value of the spring constant. And when you multiply by the displacement for what distance did you compress the spring, it will be always in meters. So the meters, they cancel, then you're left with the newton, which is N. The minus is just the direction of the force. So spring constant, you must know, newton per meter. That is the spring constant. So that K or KC, it's representing different constants. which means the value of that constant sometimes it can be 70 newtons per meter, the other one is 30 newtons per meter. They are not having the same one constant. Okay. This one.
Okay.
That's what they mean. The other one will be 30 newton per meter, the other one is 100, and the last one will be 30 newtons, since the first and the last are the same. KO, KO, AC, which meaning representing the coupling. See, they are being specific. That is for the constant, spring constant for the coupling one. And then the KO, here it's just representing the other two springs. The other two springs have a spring constant KO. If clamped, so if clamped, A vibrates at a frequency VA. So remember that frequency. Why is it VA, not F? Why is the frequency now that VA? So it's the Greek notation. We don't call it V, it's mu. That Greek letter, mu for frequency. So it's not a V, it's like this. A V like that. It's a mu. That's how they write the V. It's not a V for velocity, no. So that is the symbol which they are using. It's a Greek letter mu, which represents frequency. So you must get used to those terms so that when you see it in an exam, you don't rush. You say, why is it a V, but it's a frequency? So normally it's a Greek for mu,
Okay.
like that. The Greek letter V, which looks like a V, but it's not a V. We call it mu. A mu. It represents frequency. Any question? Yeah. Even this one is also a mu. It's representing frequency. It's not a V for velocity. Clear?
Yes.
All right. So the frequency, when if clamped A, which means mass A vibrates at that frequency, 1,81 per second. Remember, frequency is equals to what? 1 over what? T. Is that correct?
Yes, T.
They are always inversely proportional. So this T is a period in seconds. That's why we say frequency is per second. 1 hertz is just say, if I say 1 over 1 second, it's a symbol which I call hertz. Like that, hertz. It's 1 second. 1 over 1 second, it will be a second, it will be hertz. That frequency. So this one, they did not give us a frequency in hertz. They just gave us as 1 over 1,81. But yourself, you must know, if you want to find the frequency in hertz, you are going to say 1 divided by 1, what? 81. Then your answer will be in what? In hertz. If you don't want it per second, then you can use hertz. Any either you can use per second or you can use hertz. Those are the two units you can use. But the normal standard one, the SI units for frequency, is hertz, where you divide 1 divided by 1,81. Then your answer, it will be hertz.
Okay.
The basics that you must just know when attempting this problem. Then the frequency V1 of the lower normal mode is given by 1.14 per second, which means this is not hertz. If you want to convert to hertz, 1.14 per second is not the same as 1.14 hertz. If you want it to be hertz, be 1 divided by 1, comma, 1, 4. Then your answer will be in here. That is if you want to convert to here. That's how you do it. Okay.
Yes.
Question now. There we are going to write the equation of motion of A and B. That is the first thing. Write the equation of motion of A and B while it's attached to that. It's clamped to that spring constant. That is the first part. Then for B, putting W naught, that is the angular frequency, which is square root of K naught over M. K, your spring constant, that one, over M. Show that the angular frequencies W1, W2 of the normal modes. Remember, you are given the node, the lower normal of the low normal mode are given by this. So this is what we want to show. So in other words, this question is like we are doing a derivation. When you do a derivation, we must arrive here. That is what we are doing. Must be given that W0, W1, and also we must show this. So it's a matter of deriving this equation. You get it? Hello?
So at the end, we need to get the...
These values. These are the answers. So we are not calculating anything. Remember, the question is saying what? Show that the angular frequencies W1, W2, and the angular frequencies of A is given by that. Angular frequency W1, W2, and also the angular frequency at A is given by that. So we have the answer, but we are supposed to what?
To show how we got the answer.
How we arrived at the answer. You get it? So it's a good question that you have the what? The answer, but you must show how you arrived at the answer. So this is what we are solving for. In other words, we are deriving the equations of what? Of motion for the two masses connected by springs and verify the angular frequency for the normal modes and claimed oscillation. So that's what we are supposed to be doing. And once you have arrived here, then you know you are correct. Because at the end, whatever step that you are going to make, you must arrive when at this equation.
Difficult.
Yeah?
Because first, it looks difficult because first of all, we have to, we're having omega A, and then on the given equation, we have what do you call it? Omega naught. So I don't know. It looks difficult.
No, the values isn't they will change where you are substituting, where W omega naught is not a problem. Isn't it you have been given that W1 is equals to omega naught. So you use the relationships and the values they will change.
So it's not different from the one that we did last week, ne?
It's not different, but it's only that they've added other springs. So we are going to add another force. That's all. There is nothing different. The same thing. The concept is the same.
Okay.
Right. So what is it that is given in our problem? We are given two objects, A and B. You saw them, each with a mass of what? M. And then what is it that we are given in the problem? The spring constants. Okay. K naught was the outer spring constant, and Kc is the coupling spring constant, which is at the middle. The frequencies of A and B, A when B is clamped, So what do they mean by that? That the frequency of A when B is claimed. The frequency of A, remember they're saying if claimed, A vibrates at this. So that is the frequency of A if B is claimed. So B is the one that is being referred to. If B is claimed, then A is going to vibrate like that with that frequency of 1,81 per second.
So
Then
claimed as in is not moving.
yes.
Mm.
And then frequency of the lower normal mode, frequency of the lower normal mode is given by F1, which is 1,414 per second. Remember that V1, which I read like this, it just represents mu, or if it confuses you, it's just an F. It's not velocity, okay? Then the formula, this one you must always know. We know from the previous omega naught squared. What was omega naught squared equals to?
Was it R over L?
Omega naught squared, always, it's K naught over M. K naught over. Then that day we were replacing where there is Kx on the spring. That's where we came and replaced with the M omega naught squared on your assignment. Where there was K, we are replacing with this.
That was question 3, right?
Yes, so you know where you were replacing the K. The K, where was K? When you're solving for W1, W2, we replace that K with M omega naught squared. So it's coming from this standard equation, which says W naught is equals to K naught over M. So if you want W naught only, it will be the square root. It will be the square root. So you must know in a spring how you relate angular frequency, the constant, and the mass. So these are the things that you must know. Now, whenever we are dealing with these springs, we are applying Newton's second law of motion, which says F is equals to mass times acceleration, but it will be the net force. It's not just F, the net force is equals to mass times acceleration. And then omega, that angular frequency, can also be given by the formula W is equals to 2 pi F. If you want it to be like this, 2 pi F, which means 2 pi multiplied by frequency. But if you are using those Greek symbols, that mu, like which looks like V, it's 2 pi mu, which is a V which looks like that, 2 pi mu. It's still the same. Yes.
This is the V that you were telling me about. That is not velocity, it's frequency.
Frequency, which is the mu, Greek letter symbol mu for frequency. So some books, they write it like this. Omega is equals to 2 pi F, like this. And then some books, they write omega is equals to 2 pi multiplied by 1, like this mu. And so far.
Here on the other side of the notes, the one that you prepared, it's just V, the one that we know.
For which one?
No, the angular down. The angular frequency.
This one.
It's the V there. I'm saying the way it is, it looks like a normal V.
Yes. Once
Like
you confuse the velocity, then you won't understand. You'll be lost. You'll be like, which velocity? Yet you are not even talking about velocity. You are talking about what? Frequency.
It means I must just know this equation by head.
Yeah, I must know it. So it's not velocity, it's frequency, F. It's just a notation where some books, so some books just like a year, can you see what they wrote here? This one. Books, they don't write that. Some books, they write what? Mass. Some books, they write mass, for example, mass, and then they write dt of what? Of x.
Of A.
You get it? Yeah. So some books, they use this, but you must get used to the notation which is used even in the assignment. You were getting x double dot. So you must get used to those notation.
Yeah, maybe it will come like that on the exam.
Yeah, so you must familiarize yourself.
Mm.
So these are the equations, what it means. Force is equals to mass times acceleration. Especially when we are dealing with springs, we are using this formula. Force is equals to mass times acceleration. Omega, which is angular frequency, is equals to 2 pi f. 2 multiplied by pi multiplied by f. Then the mass, when we are converting this force into substituting the equation, like equation of motion of a spring mass system. That's where we are saying mass times acceleration. So it will be mass, acceleration is x double dot, those two dots, mass times acceleration, is equals to force in a spring, which is kx, negative kx. Why negative kx? Is called because it's a restoring one, restoring force. Isn't it the spring?
I have a question. Why do they use the equation of motion for spring mass system? Why do they use the x that is second derivatives?
It's the
The
why
x,
did they use x? That is the second derivative.
yes,
Isn't it? We are using this formula. Newton's second law. Force is equals to mass times what? Acceleration. So when you differentiate position,
Oh, you told us
differentiate
last
position
week.
once, you get velocity. So this is velocity. When you differentiate velocity, which means now it's double dots, you are going to get what? Acceleration.
So the first derivative is velocity.
Velocity. Then the double derivative is acceleration.
Oh,
You get it now.
yeah, now I get it.
So you must familiarize yourself with those terms. Now the first derivative, when just x, it means it's displacement. X is just the displacement. For if my spring is here, which is the mass, I moved how many from equilibrium to where I compressed this spring now. So the x is just indicating the magnitude of the distance in meters, how much you compress the spring. Then the negative, which direction? We always assume the negative as what? The left is negative. Then the right is what?
It's positive.
That's what we are doing. So which means it's minus kx. I moved the spring this side, but the force is going to push the spring back to my opposite direction. Remember, the spring wants to go back to its original position. That's why it's a negative. It's opposing my motion. It's opposing the compression itself. So the spring is restoring itself back. Myself, I pushed the spring to the left. But the spring is now resisting, going back to where it was. So it's negative the direction of the displacement. That's why the negative is coming. Isn't it when you release where you compress, the spring is not going to remain there. It's going to push back where it is coming from, isn't it?
Can you please explain that again? I don't think.
I am saying when a mass of spring is attached like that. The reason why it's minus, it's because this is the spring, it's at equilibrium, it has not been compressed. If compress that spring, now it's here. Compressed now. Let's say the spring is now compressed. Now the mass of block is there. It means this is the now new equilibrium. So what I'm referring to as our x is the distance between the compressed and the equilibrium of the initial. So this is what we are referring to x. So myself, I moved this spring to the left. But where is the force going to now? Is it going in my direction where I moved the spring, or the force is now going in the opposite direction? When I release the spring here, when I release this mass blocking, it will start to move in the opposite direction, which means it's not going to go towards the negative. It go to the what? Positive side. Then it starts to oscillate, positive, negative. So that is what they are referring to as minus the restoring force. It's opposite the direction where I compressed. That is the idea. Restoring. It's trying to restore itself to where it was. That's why the force is negative. And always when you deal with the kx, always you put a negative. Don't never forget that negative when you deal with springs. There is always a negative kx when you talk about force. So in other words, here, mass times acceleration is force. Force on a spring is minus k what? X. That's what they mean by that in simple words. M multiplied by acceleration is force. Force in a spring is given by minus k what? X. Okay. So how are we going to solve this problem? First thing, derive the equation of motion for objects A and B using the Newton's second law, which is force is equals to mass times what? Acceleration. That is the first thing. We are going to come up with equations of motion for object A and B using the Newton's second law, using this law. Yes, we are going to put everything that is happening here, we put it using Newton's first law. This force is going where, which direction, etc. Then step number 2, we are going to find the angular frequencies for normal modes, and we solve the characteristic what? Equation, whereby last time we were given a particular solution. Remember this last time whereby we were given a particular solution. Today we are not given a particular solution. You are going to give yourself a particular solution that might satisfy that particular equation. So that's what we'll be doing. Then you solve for the angular frequency. Then the third part is the angular frequencies. We are going to find the angular frequencies when B is claimed by setting xb equals to 0, which means it's not moving, it's at 0 in the equations of motion. And then
why are we using Newton's second law instead of Newton's first law or third law? Why specifically the second law?
that is the one that deals with acceleration.
Okay.
That's the one that deals with acceleration. Newton's second. The first law, when an object remains stationary, it will remain stationary unless acted upon by an external force. But the one for acceleration, which involves acceleration in the direction of the force, is second law. That's why we always use second law.
Okay.
And whenever they need acceleration, now you know it's the idea in terms of differential, you know it to be the second derivative acceleration. So we are going to calculate the KO, KC, which is the coupling constant, the values of VA and V1. Then we'll be done. So let's start now. So we are given, define the displacement of A and B from equilibrium as XA and XB respectively. So the displacement from equilibrium, what do they mean when they say displacement from equilibrium? This spring is at equilibrium where it is now. Which means it has not moved like what I indicated, stay at equilibrium. So the displacement, if it starts to move in this direction, which means K, A, I mean XA is now moving in this direction. Can you see? XB, you have compressed the spring to move in that direction. So that will be the displacement of.
So it moves in an opposite direction.
Yes. Isn't it when you are compressing the spring? The only way you can compress the spring KO using object A is to move it backward. If you move to the right for A, you are not compressing. You are pulling the spring. But if you compress the spring for B, you are moving towards the, where is it attached here? Towards the wall.
Okay.
So we have given those directions X, A, X what? B. So that is your statement or how we are going to start it. So two objects A and B, each with mass M. This is the given information. Right. We define the displacements of A and B from the equilibrium as XA, XB respectively. Then now we use the Newton's second law. What does Newton's second law say?
Force is equals to mass times acceleration.
So the force is equals to mass times acceleration. So this is the force which we are having is equals to the mass times the what? Acceleration. Okay? Equals to mass times acceleration. So now they are saying the force which is in A, this force which is in A, this side, this force which is in A, which is pulling to the negative side. That is the one which they are referring to as mass times acceleration in the X direction, which is this one, which is mass X position, which has been derived how many times? Acceleration. So that displacement, yes, it has been derived twice. So remember, our object is like this. Then we have A here, and then coupling. Then we have B. B is here, A is there, and then we have this spring again, and then we are here, like that. So this displacement, we said it's XA, this displacement is XB, which is this B is there. It's moving in that direction, the force, and the force is moving in that direction. So for us to balance all those forces, we are saying the force which is moving in the negative side, which is this one, negative side. is equals to minus KO, which is the spring constant here. It was KO, isn't it?
Mm-hmm.
Multiplied by XA, it's the force, the displacement in the X. So that displacement in the X of which ball? Of ball A. Okay? That is the first part, which is just easy, this one. Then now we are going to the second part, where we are having A, there is KC in between. So the force of A and KC, they are going to be having different directions because of the positioning of the spring. Okay, that's why here it will be minus K naught of XA. If I want to introduce KC, then it will be plus KC XA, the opposite direction. But yeah, let me use here what is given. The spring constant negative direction, KO, the spring constant multiplied by X. And where are these coming from? This one.
Yeah, that's what I want to know. Cause, hey, I'm a bit
Yeah.
confused there.
KC. Now we are done with the KO. We are here at KC. At KC, we are having two forces there.
Mm.
We are having two forces, A and what?
And B.
And B. So it is B that is pulling in the opposite one direction. Do you get what I'm saying? This B, it is the one that is pulling in the opposite direction. However, if B was not attached, it's like these forces, how are they moving? It's like this. Let's say we are having A only, like this. And this spring, it's there, it has a weight. And I did not attach mass B. If I just compress that one, there will be a force that is going to the left, isn't it?
Mm.
And also this spring is also going to the what? To the left as well. The spring, this one, also going to the, remember
Left.
this spring is a constant KC, and this spring is a constant KO. KO. I have not attached the mass B here. I'm only dealing with A. They are all moving, they are all going to move in the negative one direction. So the restoring force is going to be negative for both the spring with the KC and both the spring with the K1, with the KA. So the total force.
Sorry. If it's like this, how are you going to write the formula?
Yes, if it's like this, you are going to write it like this. So if it's like this, the total force is going to be F. It's a good question. I was going to write it like this. Mass times acceleration, two dots. Just of A, of ball A only, is going to be equal to minus K naught of the first spring, this one, constant, applied by the displacement which I moved. Remember, once I move A, I'm also moving KC with the same word, displacement. It does not change. Yes, because it's attached to the same so displacement of ball A. which is also minus, because it's in the same direction, K what?
C.
Multiplied by X what? A. Remember, I did not attach anything to that spring. It will be like this.
Okay.
Because of introducing this spring. Okay. But because I have added another mass here, this one, and this mass which I've added is not attached here. It's pulling in the wrong side, in the opposite one side. And all of these you are seeing they are negative. So which means that spring which I'm going to, the mass which I'm going to introduce, it's mass what? B. And I'm going to compress it not with an XB, XA, but it's going to go in this direction, which is opposite the other forces. That's why we are going to put a plus. What is the constant for that spring mass? It's Kc. Yeah, Kc.
You said, sorry, you said why did you add the plus? Because
Xp. I added a plus because this force which the ball B, where it's compressed, isn't it attached this side? It's not going to move to the left. It's going to move to the
to the right, towards the wall.
because,
On the
yes,
right.
because that's where it's complete.
Okay.
When you compress it, you are going to move it to the right. Since we said the negative is this side, the positive is that side. That's why the equation is like this. And then here they just rewrite. So at first you can write it like this without the brackets. You say it's mxa is equals to, remember there are two dots there, mass times acceleration for A only, minus K naught multiplied by XA minus Kc, which means the constant in this spring multiplied by displacement XA, plus, it's showing you that because there's a ball that has been attached, so it will be plus Kc multiplied by XB. That is the equation. And then by factoring out Kc, that's why they started to write XB minus what? XA. Can you see where it's coming from? They factored out K what? Kc. Between these two, they factored out Kc. If you factor out Kc, then it will be positive XB minus XA, just like this. If you factor out Kc, you are left with the XB minus X what? XA.
Okay. The first one, the K naught XA is going on on a negative, on the left direction. Why? That's why we write it as negative K naught XA, ne? Okay.
Yeah, that is
So
the first. And also this Kc.
Yes, you can explain. That's what I want to hear. The second part, the KC. Why
Kc,
is it also negative?
because the spring is attached to A. This spring Kc at the middle, the coupling is attached to A. While we are ignoring this mass B, at first we ignore the mass what? B. That's why we say that they are also both going in the negative direction. Remember, the spring is not attached to anything on the right. The spring is not attached to anything on the right. It's just like this. Just like this. Then you have your A. Then you have your coupling spring.
Yeah.
That. So it does not cause any force to the right. all the forces will go there because there is nothing resisting the motion, which is going to the left. So if this A naught, AC, this is your A, any displacement that you are going to put, even this one, KC, will follow as well. That's why we are saying it's minus K naught multiplied by X what? A. Minus as well, going in the same direction. Why are we minusing? It's plus another force, which is also going in the negative what? Direction, which is K, C, multiplied by what? X, A. And then using your integers, positive, negative, it will just come back to K naught multiplied by X, A, minus KC multiplied by X what?
A. So when we pull the string K naught towards the left, so also KC A also moves towards the left.
Yes, it's a spring, isn't it? It's a spring.
Because
Yes.
they are attached.
They are attached. Yes.
But
That
B
okay.
does not move.
While it's claimed. Then now we put the mass B. The mass B, remember, it's there, isn't it? So now when we add this B here, when we add B, we are now adding B. B is now attached to the right. How does it affect our equation? It affects our equation because the direction where B is claimed is to the right. So this is connected to the right, which means it's not going to move to the left. It will resist the motion of going to the left, which means it's also pulling to the what? To the right. There is a force that is pulling to the right. So the force that is opposite of negative is a what?
It's positive.
Positive. And what was the spring constant here? It's K what? K naught. So it's K naught multiplied by X, but the X is with respect to the mass what? B, not mass A. That's what you're just saying. That's what you're just adding. When you add this mass, you also add the plus, then you introduce that. Any question? Because we are here. That's where we are. Explain this one.
No, I think I'm clear.
Then you do the same. You apply law of motion to A. Then you also apply the law of motion to B. You don't only apply to A only. You apply to A, you also apply to B. So now we want to do the same. What we just did to A, we are going to do it to what?
To B.
To B. Yes. So that's what we are doing. So that you don't memorize these things, they must just flow. You understand these things, what you are doing. If you understand, then you find them easy not to memorize. Right. Now let's go, we analyze it B now. We are done, we have applied the law of motion at A. Now we are applying the law of motion at B. This is my B. We are applying the law of motion at B. We are here.
Okay. So the equation is still the same. It's just
the equation is still the same. So what you are, it's just like this. This is now your B. You have your mass like that, and the spring is also hanging. You have not attached A there. So this is your B. You have not attached what? A. So you use the same formula. mass times acceleration at B is equals to, always, you always start with spring constant restoring force. I told you it's what? Negative. Or if you want it not to confuse you, let's do it like this. The position where B is exactly, we put it there. We do it like this, so that it does not confuse you. Then this is our mass B. And then this is the spring. It has not been attached to anything yet. So here we are told this is K what? Not. And then this is K what? B. Our motion is going to move which direction? When you compress towards this.
Towards the wall.
Yes. So which means the mass times acceleration at B will be equals to, the force is minus K naught applied by the displacement, which is what? X what? B. And also this spring is not attached to any mass. It will also move towards the same direction, which is minus K C applied by the same displacement X what? XB. It's also moving towards this side. So this is our negative side, which we are saying because it's restoring force. Then we introduce a mass. Which mass did we introduce? We introduced a mass A. So we are going to put a mass A, which is here, this one. The mass A. That is the mass A that we have introduced. So how does our equation affect? A is connected this side. So which means it's going to pull toward this side, which is the opposite. What is the opposite of negative? It's what? Plus.
Positive.
Positive K what? Which is K naught. It's right here. It will be positive. It will be positive what? The spring constant, Kc, multiplied by X1, A. Can you see the difference?
So step 2, okay. You got the first
Equation.
where which is A.
Yes.
And then you got the second equation. Right.
Here they just factorized, but you can still leave them in while they are not factorized. Still correct. Here they just factorized.
No, I think it's more clear when they factorize. It's making sense.
It makes more sense, yes. Because Kc is common. Then when you factor out, it will be, you start with the positive. It will be Xa minus what? Xb.
XB.
Yes. Any question?
No, that part I get it. I understand.
Right. So now we are going to the second part. We rewrite the equations of motion, which means this is the first equation that we got for A. We equate it to what? To 0. And we rewrite the second equation of motion. We equate it to what? To 0. So these are our two equations of motion. What are we supposed to find from these two equations of motion? What are we trying to solve? That is the question. We are going to solve those two equations. So we assume solutions of the form AX. A is equals to A to the power I omega t. It's a complex. The complex root to this one. Which means this is a root where we were having that other day where I was telling you if it's a solution to this differential equation, when you substitute it back here, it will satisfy the what?
The equation.
Yes, like what we did the other problem. If you take b, put it back into the equation, it will satisfy that equation. So the x which they are talking about, it is that will satisfy that equation. That x will have that form where xa is equals to a is a constant. So a is always a constant. E, it means an exponential to the power I, which means that complex, where I, we know square root of negative what? 1. That is I. Remember, square root of negative 1 is what? I. You know it now, it's complex. So that is I omega t. Or omega t. So that will be the solutions that are going to satisfy those two equations. What do they mean? For xa, it will satisfy the first equation. For xb, it will satisfy the second one equation. If you put it back, you will find out we are going to get the answer 0 then. So now they are saying substitute the equations of motion and divide by what? By e exponential e to the power I omega t. So which ones are the equations of motion that we have substituted? Mass times acceleration, where there is acceleration, this one. We are replacing.
So when you wrote the equation of motion, did you factorize it? Because now it's a bit confusing.
The equation of motion?
Mm.
All right, let's rewrite it. XA, check where XA is.
Okay.
What did we start with? Mass times acceleration. So by equating it to 0, we moved everything towards the what? MXA. So K, can you see? K naught XA, and then which one is having XA? You take another quantity that is having XA, which is KC XA. Are we together?
So the ones that were negative, and so my you know where my confusion is, the force there, FA, MA, the one that, yes, the first one, the mass and acceleration. Why is it still positive, but the rest of the things changed? Because it was positive before, and then when you equate everything to 0, it's still positive.
Which one? The mass times acceleration?
Yes.
Yes, it must be positive. Why must it be positive? It's because we are saying mass.
Force can never be negative, ne?
No, it can be negative.
It can.
Yes, force can be negative, depending with the direction. Because this force which are dealing with is negative. We are saying mass times acceleration is equals to that K minus K naught. When it comes to the left, it becomes plus what? This K naught X, it will become plus. It's coming to the right-hand side, to the left-hand side, sorry.
Oh, that's why the mass times acceleration didn't.
Then the KCXB, it will be minus.
Now I see it.
Now you see it, isn't it?
You took it to the other side. You took the force to the other side.
Yeah. That's what is happening. And then on the right-hand side, you are left with nothing. So that's why we are equating to 0. We do not just equate to 0. We moved everything what? To the left, so that we can get the right side equals to 0. It's still the same equation, but you just rewrite. So what we are going to do next is to substitute this equation. So we are going to do like what we were doing the other day. You say mass times acceleration for the first equation, which means you differentiate like what we're doing, where we are given XA is equals to A e to the power I omega 1 t. If I say x dot, you are differentiating this with respect to time, the first derivative. So we are going to get A I omega e to the power I omega t. Is that correct? When you differentiate the first time. Do we agree? How do you differentiate an exponential with respect to time?
Don't you introduce ln?
It's differentiation. E to the power x. E to the power 6t. You differentiate, you get 6 e to the power
60, yeah.
That's how you differentiate. So we are applying the same principle here. When e to the power I omega is a constant. So this I omega is a what? A constant. So you multiply the constant here outside, and then you repeat it again, put it there, the first derivative. Then you find the second derivative, which means how many dots? 2. To be equals to. You are having AI already, so it will be AI squared. Can you see? W squared, which means now we are repeating it, multiplied by e to the power I omega t. So that's where this is coming from. I squared. What is I squared? Square root of -1 squared. It's -1. So it will be minus a multiplied. The minus is coming from I squared. I squared, you square here, you square, you are going to get -1. So that's where it's coming from. So negative a. From negative a, then we are having omega squared. This is your omega squared. This is your negative a omega squared. E to the power it. E to the power I omega t. That's why they say divide by it. You differentiate, then you divide. When you divide by that, which means you are going to cancel it out. This one, when you divide by that, then you'll be left with minus m mass times that acceleration. It will be now a negative a omega squared. That is the one which they replaced here from the original equation here. Instead of writing xa, now they put m omega squared, like what we're doing in the previous assignment. Where there's k, we are replacing that one with these values. Where there was x, m omega squared. Then everything stays as it is, nothing has changed. KCB, you do the same here. You are also going to get minus here. When you differentiate the same equation, xb, first time, the only difference is that here there is now a b. Here there is now a what? A b. Instead of a, you are now having b. We'll be having B here. That is the only difference. We're having B as a constant. That's why there's a B now. So now we want to solve for the constants so that we eliminate the values A and B. These are the values that we want to solve, to remove this A and B, so that we find what are the equations for omega, and then we can solve. So let's see now.
Sorry, didn't we exceed time? It's now 8 past.
Oh, all right, it's fine. So what I will leave it for you here. When you are given this equation, like here, isn't it now we want to solve for omega 1? It's now a quadratic equation. Both of them, they are quadratic. So we want to solve for omega 1, omega 2. This is what we are doing here. So from this equation, if you are given these two equations, how will you solve for omega from these two equations? You can just copy them down so that you can you recap when you're coming.
I took a screen.
Yeah, no problem. Yes. So these are basically the steps that we're just doing. Finding those two equations, we rewrite so that we can solve. Because the idea we want to solve for W1, W2. Where is W1, W2 coming from? It's coming from whenever you have a square root. You have two roots, isn't it? The first root, that is the one which you are calling root number 1. The second root, root number what? Number 2. Can you see? So what is more important is for you to get to here. Once you are here, then we can solve. So where we are going to start tomorrow, we are going to start from here, solving this equation so that we get our roots. But I think from getting this up to here, you should have understood now.
Yeah.
Where we are getting this OA minus M omega, they said you differentiate and then you divide by E I omega T. So you must try it by your own without looking at the answer, whether you see you are getting the same value here by just differentiating the first time, second time.
Okay.
We'll stop here, we'll finish it. But you can see these are long derivations, and when they come in an exam, they'll be having a lot of marks, 10 to 15 marks, and it's a lot.
It's a lot.
Okay. So let's wait here for now, then we'll complete it tomorrow.
No problem. Please, should I remind you tomorrow for the videos? Because I think now it's late. I mean, after the lesson,
once you are done, you can still remind me, no problem.
Okay.
Yes, so that you can catch up where we left here.
No problem.
Okay,
thank you.
Otherwise, it's late. You might think that there's no class.
No, I think I'll remind you tomorrow, maybe in the morning around 10 or 11.
Okay.
Yeah. Okay, bye.
All right, thank you.